Hi all, this is Claudio from expertfea.com with a new live stream. This one regarding the impact of bullets in explicit dynamics. So I opened ANSYS Workbench. Let me also share my screen. A small reminder, you can find us at expertfea.com with lots of simulations, books, FEA support, and video webinars and live streams. So this is ANSYS Workbench. This is another domain than static, structural, and transient structural. Explicit dynamics allows mesh erosion. Here, breakage will appear, also fracture. Now I observe that the microphone was far away. Let's recap what I was saying. We're going to work in explicit dynamics because it allows mesh erosion, and we will have the bullet penetrate the impacted parts. So let's go for the first time. Let's design something. Let's model something simple. It's the FEA in principle is pretty straightforward and simple because we have the bullet impacting either one or more parts. And we will kind of compare the difference between various types of meshes and various material types. So let's see how should we model the bullet. Should we use a spline or an arc, or let's see with the spline if we can do something. Ooh, this looks very nice. Should we leave it like this? Yes. Escape. So we have this profile. Let's close it. Then we're going to revolve it. Design, we're already in the pull command. We have revolve. We're choosing this axis. Select one or more faces to revolve this one. And we can click here, which will be 360. Look, we kind of have like something like a bullet. It's a little chunky. Let's undo a little, Ctrl Z. Ctrl Z again. Can we do something here? Let's see what can we do. If I move this, all right, and this. Let's enter the move command and move this point a little. I don't like my bullets chunky. All right, so we have the trim command here. Again, on 3D model. We'll repeat the pull command, then full pull. All right. It is something. Let's pull this if possible. Escape. It will be pulled. I don't like to continue the curvature. I would like to pull it as a cylinder if possible. The easiest way is copy paste. Control C, Control V. Let's see if it works. Yes, it's something like this. All right. What do we do? In order to look nicer, we will apply a radius here. We're already in the pull command around. How much should it be? How much? Come on. 5? No. 10? No. I think we're limited to undo. All right. So this looks kind of acceptable. This peak, this point, it's too fine for my taste. Let's select it. Can we pull it? Can we round it somehow? If not, let's do it in Sketch. Okay, Control Z, undo. Let's see if we can somehow round it. We have here the rounded corner. Does it work? Not so much. All right, I think we are overcomplicated. I am overcomplicating this. Should I do it like this or not? All right, maybe with a radius. With a semicircle. Come on. But if I round it from at this point, it will not be correct while we're doing the revolve. All right, let's stick with what we have. Copy paste, and we are training this. How much? 1.5. All right, perfect. You know what? Let's not waste too much time. We're going now in sketch mode, and we will be making a plate. But because I want it perfectly symmetrical, let's create a plane. I'm clicking a face, then clicking the plane button. And I will be moving this the closest to the pointy thing. Maybe something like this. Let's see. All right. Something like this. Remember about Control middle mouse and Shift middle mouse. All right. So let's make the one plate as symmetrical as possible. We don't want it to be too big, because we're interested only about the region with the impact, with the bullet. Let's make this, 15. Tab, 15. Now we have a square. I don't know if we are perfectly. No, we're not perfectly symmetric. Because this is 8, I think. Okay, yes. Let's make this 7.5. 7.5. All right. Do we have here 7.5? We have 7.5. All right. Let's see this dimension. It's not 7.5, but let's make it 7.5. Enter. Now we have a perfect square, I think. So how thick should this be? For example, this distance is 1.5. 1.5. Should we have it 1.5? Yeah, why not? Let's make it even 2. Because the arrow points on the opposite side, we will write from the keyboard -2. Ooh. Maybe 1.5, maybe, okay. Should we make these small plates bigger? Yeah, why not? Also this one to kind of look like a bullet, let's say. This one, how round, how much roundness? All right, and let's duplicate these plates. Triple click to select solid. Triple click. Move. With Control pressed, we will duplicate. We'll make copies. Control pressed. All right. Let's go here. Control pressed, and we drag the desired axis. How much should we leave? I'm thinking about some of the parts will contact this plate, some of the chips. Let's make it 8. And with Control pressed, we can do the same thing again. And we will write from the keyboard 16 to have the same distance. Is this enough? Or should we go further? Let's leave it like this for the moment, and also make the plates a little bigger. So we select the faces that we need with Control pressed, and with pull we prescribe a value, and it will extend in all directions. Okay, let's say the normal positive side of the selected faces, something like this. Should we make it maybe 2? All right, 2. Because I would like to compare more, let's say, 2 scenarios. I forgot to resize these ones. No problem, I will just duplicate this. Triple click, move, Control pressed, 8. And again, I will write 16 to keep the same distance. All right. I would like to make a mesh comparison. This is why I would like to select all these and kind of move them on the Z, on the positive direction of the Z-axis. Move with Control pressed. Yes. 21, why not? 20 because it's round. Something like this. Should we leave some space for breathing? Okay. Let's not suffocate. What do we have here? All right, I think we are done with the modeling at this moment. Let's name it stream 4. January 5. And name it simply bullets. So tomorrow on the 6th of January, we, let's say, celebrate 13 years of expert FEA. And yes, we are happy. Let's see if we have a welcoming message from anyone. Not at this moment. Okay, this is the geometry. Let me close space clean. And what we're doing now, let's insert some materials. All right, engineering data. Should we work with steel? Let's work with steel. But we will assign different types of steel also. So we have the linear steel, let's say. Let's assign also a nonlinear steel from the general nonlinear materials library. And also let's assign a steel from the explicit materials library. All right, let's go for steel. There are various types of steel. Which ones should we choose? So, for example, this steel has defined some Johnson-Cook strength. Look here, hardening exponential. So we will have plus deformation. Let's look a little if we have, we also have these types of steel. This is defined only with shock equation of state. This is defined also with Steinberg-Guinan strength, hardening exponent. So much and so many to choose from. I like these curves, stress strain curves. So we have one with Johnson-Cook. Let's add it to our library. And then let's go, do we have something different? Steinberg-Guinan. At this moment, let's stay with what we have. So we have three types of steel, let's say. The elastic one with only isotropy elasticity, the one with plasticity, which is defined here, bilinear isotropic hardening, besides isotropic elasticity, and the one that we have here, defined with Johnson-Cook strength, and we have the plasticity defined here. All right, let's use these types of steel. Where? In the plates. This is the material for the plates. Let's see if possible. The material of the bullet usually is lead, I think, bullet tip material. Polymers, lead alloys, hollow point stabilization. Okay. The problem will be if we make this very soft, then we cannot penetrate too many steel parts. This is why also when I gave that like a trailer for the live stream, there were some very thin boxes, let's say, yes. Where are those boxes? Come on, show me. Yeah, something like this. They were very thin. And being very thin, maybe 0.1 millimeter thickness, even lead bullet, lead tips or copper tips can penetrate them. But if I leave the materials, these ones, to be steel, then having this lead or copper, it will be very hard to penetrate them. Either we're changing the materials from these to aluminum, or make these plates thinner, okay? You know what, let's go for aluminum in order to, because it will be more spectacular to break, let's say, thicker plates. Let's do it. So scrap the steel thingy and add, we're talking now about the plates, yes? Aluminum alloy, linearly defined, without any plasticity. Aluminum alloy, non-linear definition. Look here. We have here the elastic and plastic domain. And from the explicit materials, let's assign, we have this thing with Steinberg-Guinan strength. This one is very simply defined. Do we have Johnson-Cook? We have Johnson-Cook, all right. But I think this is a stronger, this is a stiffer, I think, alloy. Let's go a little here. No, this is explosive. HE, I think, means high explosive. Yeah. Johnson-Cook strength. I like this. What is aluminum? Bilinear isotropic hardening. So look here, we have plasticity, also a shock equation of state. Yeah. So at this moment, also Johnson-Holmquist strength continuous. Oh my God. It's very nice to have where to choose from. And let's keep three densities. And I would like to have some lead or copper. Let's see what for the core, or in order to run the entire bullet due to density malleability. Yeah, let's go for lead. Lead defined with Steinberg-Guinan and shock QS. Bilinear isotropic hardening. This I like this at this moment. This will be for the bullet tip or core. I'm not an American, so I don't know too much about guns, because they are not, let's say, ready for purchase in my country. Let's make some definitions. This will be bullet minus Z, because this other one will be bullet plus Z. You can look here on the Z-axis. All right. The other ones will be F2 plate. All right, the bullets, I wanted to make them of lead, and these other ones, let's make something like this. Should we make a third scenario? A third type of, yeah, why not? We are not pressed by anyone. The more the merrier, yes? And a little, maybe let's make the plates a little thinner, a little thinner. So I will select these faces with Control pressed, these faces with Control pressed, these faces with Control pressed. Look here. And I will go on the pull command, and with minus, we will insert a value. How much? -1. How much will be -1? Yeah. So in reality, now it's 1.5, I think. Oh, 1. Okay. Yes, let's make a third scenario. There is a difference between selecting from the left, yeah, and selecting from the right. The right selects everything from the right in a space claim. Just keep this in mind, okay? So let's select from the right, move, Control pressed, and we're dragging this. How much should I drag? Because I didn't measure. I don't know, maybe 22? Yes, 22 it is. And I didn't, being transparent, we see that they are shell bodies, yes? So I didn't select everything as a solid body. There is a very quick workaround because I don't want to redo. We have repair and missing faces. They will detect them, and that's all. Let's save. We'll leave it open because I would like a faster update geometry from source. All right, so now I can close space clean. And let's locate the bullet, the third one. It's called, now it's, I'll call it bullet Z, and this bullet plus Z, okay. All right, and these F2 rename plate, but they will assign the wrong naming, I think, the wrong numbering, yes. It will not continue the renaming. The easiest is to select all these and rename them again, F2 plate, and it will assign correct numbers, let's say. Here at the plates, let's make these out of simple aluminum. Let's make these out of aluminum alloy NL, and let's make these out of aluminum 2024. I do not expect much difference between this one and the nonlinear one because it has bilinear isotropic hardening defined. I was under the impression that it has also bilinear isotropic hardening, but not only Johnson-Cook strength. Perfect. So bullet minus Z. It's all bullets are made of lead. Connections. You can see by default we don't have contacts, we have body interactions. And it's kind of frictionless. Let's see what friction coefficient. I think it would be pretty big. Lead, aluminum, friction coefficient. It should be pretty high, exceeding 1. Oh, 0.95, 0.3. All right, so let's assign here instead of frictionless, let's make them, I don't know, 0.9. I feel confident with 0.9. Save. Let's look at the mesh. The mesh by default is linear. I talked, I think, in the first live stream, I talked about the difference between linear and quadratic. And here we have we don't have mid-side nodes, let's say, yes? So let me tell you what I mean. Let me tell you what I mean, but if we change the cursor mode to node, you can see that we have nodes only at the intersection of the, let's say, the edges. Yeah, we don't have nodes in the middle. We don't have nodes in the middle. Wherever we go, we don't have nodes in the middle. This means that this edge, let's say, is defined by a first degree equation. Hence the name, linear, okay? It's a simple line. If we were to have quadratic, then we would have had a mid-side node. Yes, I can show it to you because it's very quick to see. Look here. I don't care about this mesh at this moment. I want only to explain to you. Cursor mode, node. Look here. We have more a node here, as expected, and also in the middle. Yes, also in the middle. Yeah. Look here. Even though it's failed, we have no node in the middle. All right. Let's go back to the default linear. Generate mesh. What I do not like is that the bullets are too big compared to the place. We should choose something. By themselves, the bullets are pretty small, I would say. So, you know what? Let's leave them like this. In principle, I like working with tetrahedrons because these will not break so nicely. But let's just solve it, and you will see what I mean. Yes, because they will not break so nice. You will see what I mean. Here, I usually on sizing here I go to not capture curvature. No. And on quality, I am going for smoothing low. Element size, instead of 1.8, let's make, I don't know, maybe 1. And let's see what will. Ooh, yes. Below 10,000 nodes. All right, let's see how nice will this behave. Save. What do we need to do? two options. The most realistic option is to apply initial velocities. And this is what we will do. Change the cursor mode to body, and we will apply initial velocities. What is the initial velocity of, bullet speed in meters per second? All right, how much? Exactly when it gets out is 120. Handguns, 360. You know what? Black powder, we don't care about these. Let's do it something like this. Okay, 350. 350 is my assumption. We have multiple methods to define the vector. One of these would be something like this. And we can click here to change the direction of the arrow. Yes, apply. And it will be, if we change here, just for understanding, if we change here to meters per second, 350, all right? But I'm usually used with millimeters, and it will be 350,000 millimeters per second, all right? So we have the velocity now. Because the plates are kind of drifting into cosmos, let's fix their peripheries or peripheral faces. Control F to select only faces. If we click any arrow, we can reposition, redirect, let's say, the views. And yes, let's go here for fixed. And we will be selecting, because we don't have proper selections, yes. Please look, I put mine here, I customize it. Please look for the box select somewhere, or in the middle mouse, or in the selection. You need to be on the box select, and you have something like this. With Control pressed, we select these faces, and you can see, yes, they're selected. Also, we will reposition them like this. I'm clicking the Z axis again with middle mouse and Control. Look, everything is selected. Apply. They are fixed. We have the initial velocity perfect now. We almost have everything. Let's calculate a little, just a little. Because we have to travel a distance of around 30 millimeters, let's do a rule of thumb, or I don't know how it's called in English. Yes, so they travel 350, yes, 1,000 millimeters in 1 second. But how much will it take to travel only 30 millimeters? How much will it take? Maybe X amount, all right? So now we know that X equals, there is this diagonal, 30 millimeters multiplied with 1 second. I'm explaining it very, very easily and very clearly. And please always use your units, your measurement units in your equations. Always use them. 350,000 millimeters. What we can do? We can remove this, simplify this. We will also remove a 0 from here and a 0 from here. and the second will stay. This is not 15, this is a second, all right? So x equals 3 over 35,000 seconds. If we pull up the calculator, 3 over 35,000 seconds, we have 8.5 minus 5. E minus 5, all right? This means it's very close to 1 E minus 4, yeah? We can write this here, 8 point, let's say 6. I will put here an approximation sign. 8.6 E minus 5, or x equals, yeah, approximately 8.6 for certain people multiplied with 10 at the power of minus 5. Yeah, or 100,000 below the fraction if we will do a fraction. We don't care too much because we will further go and approximate it with 1 E minus 4, something like this, all right? Second and second. This will be the timing, the end timing that we will use here. The end timing, yes? We'll put here 1 E minus 4 seconds. Now, should we leave them by default? Let's leave them default at this moment, these time steps, even though I like to customize them. What we need also to take into account at this moment, we will play soon with this geometric strain limit. Soon we will play. In order not to have those red spots that you see. Some people have some red spots. Let me show what I'm talking about. Bullet ANSYS, you will see it, I think, very, very quickly. Also, I have them. Look here. There are some red spots, yes? These are the mass centers for the eroded mesh. They are clearly more clearly seen here. Yeah, you can see these red spots, which appear when the mesh or the elements are removed, yes? So in order to remove those red spots, you need to make this no. Retain inertia of eroded material, no. Yeah? Also, to have a finer animation, I usually make here 100. Feel free to make it whatever you want. Save solution information. Let's go with deformation stress. Control, right click, switch to automatic mode. And here in the solution, we can choose anything and everything. Total velocity and total acceleration. Why not? Stress, also plastic strain. Let's solve them. I'm curious how much it will take to solve, because if it takes too much, I will make the mesh more coarse. I cannot afford 50 cores here. I need to put 8 cores here, because there is no difference with my licensing between 8 and 50. Having above 8 cores will slow the solving. It will take more time, in my case. Let's see if the FEA starts. 15 seconds. Yes, we can wait 50 seconds. Why not? Maybe 20, maybe even 30, maybe. Let's see if we have any question. Yes, we have a question. We can also salute. Hi, singing fingers. Because, you know, we know each other from yesterday. So his question is, in the near future, I would love to see your tutorial on shape memory alloy, like the paper clip return to its original shape after being bent. Is it possible to simulate that using ANSYS? Yes. I think maybe you're talking about some heat also being applied, maybe, because you can simulate it with at room temperature and also when heat is being applied. It can be done. I will think. I will meditate a little. Meanwhile, look at what I have done with the shape memory. I think I have done one simulation, I think. Did I do or not? It kind of escaped. Maybe I called it SMA. SMA, maybe? No. Shape memory. I didn't do it until now. All right. It kind of escaped my mind. Peeling with, yes. I remember having done something with shape memory alloy. Let me look at my website very quickly. And maybe I will. Now that I think about it, I think I didn't make it. I made it for some articles for some scientific papers, and I didn't publish because I have used that model on some articles. So I think, yeah, I think it's not made here. So yeah, it's not made. It's in a scientific paper. Do you have a reply now? Yeah, it. Let me think about. Let me think about it. In the meantime, there was. You can find on YouTube. I will. You can find something on YouTube, I think. But yes, it's good that you told me. Look here, it stopped at 42%. Why? Problem terminating insufficient memory in contact. All right. Let's hit save. Where is the problem? The problem is where we predicted. I predicted. I mean, where we have the linear aluminum alloy. Yes, no plasticity is defined. So this is not correct or cute or nothing. Yes. So just for fun, let's make a cross section to inspect things here before this artifact appears, these errors. Right click, retrieve this result. This is made with the aluminum alloy nonlinear with bilinear isotropic elasticity. How is it spelled, bilinear or bilinear? Bilinear, okay, bilinear it is. bilinear isotropic elasticity, and this is with I don't know, Johnson-Cook or something. Let's see. Johnson-Cook, yes. So we begin to see fracture, yes, because we used properly defined material for such a load, for such a quick time event, yes, in explicit dynamics. Also, what we can see, we need to refine the mesh. Look here, yes, it's the elements are going to be too big, and because I have my doubts that at this speed, I will not interfere with the speed. I have my doubts that at this speed, they will penetrate more. I will make the plates a little thinner, okay? So here we have the confirmation that elastic aluminum alloy is not correct. Yes? Let's animate just for fun. I have excluded this portion with the error. All right. So now, what are we doing? Let me, you know what? Let's exclude from the start the linear aluminum and maybe put another aluminum. You know, something weird like Holmquist or Steinberg-Guinan or something, because we have plenty to choose from. So aluminum alloy nonlinear, I will just delete it because it is possible. This is bilinear isotropic hardening, and this is Johnson-Cook. All right, let's add another aluminum. Steinberg-Guinan, Gruneisen, perfect. And I will select it. I will select it here. This, they have lost their aluminum, and I will apply 1100. All right. Now we have, I promised thinner plates. Should I keep my word or not? Let me keep my word. Why not? Firstly, let's solve it quickly with these three aluminum alloys defined non-linearly. This is why it's nicer to work with the explicit dynamics. The solving is very fast. Where is the problem? Here we should have 0, enter, right click. I wanted to click evaluate all results, but yeah. So this, I told you in the beginning, having a pointy thing, I don't like it so much. And also the mesh, because this pointy thing goes exactly in the middle of an element. And in principle, it does not find a node there. There are some integration points. For the one who is interested, they should go and check the difference between an element node and integration points. Inside the element, there are integration points. So let's make the plates thinner, and the FEA will be nicer. Because we're on the right track, we're going to duplicate this. Any other question? No. Okay. Let's make the plates thinner. You know, we want to captivate the audience, and we will do something spectacular that appears to everyone and anyone. So I said that the plates should be thinner. Let me select them with Control pressed. You see them? And we're going to write a value 0.5 with minus in front of it. 0.5. All right. And now let's move a little, all right? I will move these upwards with how much? 2. And this with 1. All right. Let's see if I can. Let's see if somehow I can. Make the pointy. Let's see if I can make the pointy thing. If I can cut it a little. How should I cut it? You know, let's convert this this edge. Let's create something like this. We don't care how it looks like at this moment. What I would clearly like to do is to make like a radius or something. How should I do this radius? Something like this. So let's trim. I want this to be a part of my profile. I think this should be nice. And here, also this small portion, if I have it, I don't know if I have it. Do I have this line or not? This should be a curve in my assumption. This should be a curve. You know what? Let's convert this again. This portion I need to be cut. Yes. Let's see if I thought about it correctly. So design, pull, revolve. This is the axis and this is the face. I will click here, cut, and complete the cut. So we have something. I don't know how cute is it, but yeah. Let's round this a little. Something like this. I don't know if it's a revolution or not, but you know what? Let's leave it like this. Triple click, delete, triple click, delete, and I will copy it. I think it was 22. Let's see. 22, yes. This means we can also do here 44. Right click, show all. When you click here, when you uncheck, you hide or unhide. Just saying, yes. When you uncheck here in the tree, right click, show all. Save. Here, double click. Yes. So we have here, this is called it was bullet Z, but now it's bullet, and now it's bullet plus Z. These are made of lead. All right, let's always check what we have here. Generate mesh. Yeah, I think that peak, the point that does not even exist of this quartz mesh. All right. Now I would like to get rid of the hex mesh at this moment. Let's solve because it goes so fast. Do we have applied the velocity? Yes. Let's apply it also here. Control B to select bodies. Apply. Save. Let's solve them. And we can make such iterations and compare with what we had in the past. Clear generated data, yes. Solve. Clear generated data, solve. It's snowing outside, -3 degrees. Clear generated data, yes, solve. Always look at the time increment. Yes, so it's very slow, very small. So now we have thinner plates. So the aluminum with the let's let's see what properties have. The aluminum with Steinberg-Guinan. Broke a little, but not too much. And the aluminum with Joseph Cook broke much, all right? The aluminum defined would be linear isotropic hardening did not behave correctly, okay? We should have breaking. I think I promised some time ago a section view. Let me keep my word. Click Edit Section Plane, and I will select this part in order to have this displayed like here. All right, so let's save. And animate. You may be asking yourself, hey Claudio, why do we need to have breakage here on this plate? Why? Why is it mandatory? Because we are going to take a look at the stress. Look here. It has the highest stress. Yes, let's scope a little. Probe. Yeah, and the aluminum thin plate should be broken because we exceeded the ultimate tensile strength. If we look here at the aluminum alloy NL, the ultimate tensile strength is here is around 290 megapascal, 290 megapascals, and we have here how much? 640. Yeah, it's no excuse. It should break. As simple as that. For example, yes. Here, it's after breaking. Yes, it's just normal. If we let's duplicate without results. If we are going to solve it a little before, yeah, we have this. If we are going to here to retrieve this result, you can also see here an increase in stress. Yes, you'll also see before it breaks. Look here. Let's right click, change the cursor mode to know that. Let's leave it like this. So I think these values mean, yes, they mean that they will crack in the future. Let's animate a little, just a little. Yes, it needs to be debated. Which one is more correct. Okay. My assumption is we cannot have reliable discussions and results with such a coarse mesh because it does not make sense. This to have 100 below 200 megapascals and this to have 500, and it doesn't break here. The elements are elongated too much, all right? Why are they elongated too much? By the way, I would like to propose an answer for this. Please keep this into account. And this is kind of a big secret for ANSYS Dynamics. The strain limit, the elements are allowed to easily deform, to dilate 150%, yes? To dilate 50% more than what they have. So just take these into account, because we will be changing this very soon. At this moment, let's refine the mesh. Overall 0.5. Yes. And because we have, I think it works. Sincerely, for such a behavior, I don't like these hex elements. I would like, and I think tetrahedrons will encompass, will describe even better the phenomenon. Okay. So this is kind of overkill. Let's make this again 0.75 maybe sizing. Yes. At this moment, we're mostly interested in these plates, all right? So save and solve. Such discussions should be made when investigating bullets and plates and everything, discussions regarding materials and the mesh sizing and the resulting stress and strain, and yes, and also correlated with pen and paper with the theory. If you are desperate and you have problems, you can make this value 0, maximum energy error. Yeah, at desperate times, okay? You can take a look at the time increment. We can see some similarities to what we had in static. I mean, is a fraction of the m time, yes? The m time being 1 minus 4, then the time increment can go below, yes? Much below 1 minus 4 to be the thousandth time a fraction, a very small fraction of the m time. Here, let's make this 0 again. Evaluate the results. What we're beginning to approach something decent. Equivalent stress. Let's probe a little. Again 140 and again 400, 500. And here, ladies and gentlemen, I think we begin to have fracture here with the bilinear isotropic, bilinear isotropic hardening. So 150, 600, 450, all right. And let's change now the meshing to be tetrahedron overall. All right. So the easiest way is click one body, Control A to select all, Control A, apply, and it will be everything tetrahedron now. Of course, if we assign a tetrahedron, generate. You'll notice an increase in the number of elements, and usually it solves a little slower. Should we go even fine? Normally, if you remember, we should have 2 elements per thickness, if you remember from the past, from, I think, from stream 3 or 2. I would like to go with 0.4 here. You know what? Solve it with 0.5 with 1 element per thickness of plate, then with 2 elements per thickness. This is 1 element per thickness. Yes? There are 1. Let's solve this. Be curious and make such, and you know what, vary the input, either the mesh, either the velocity, either the material, either time step, vary, and be creative and look for workarounds and solutions, and just play. Okay, I'm talking about in the beginning. Yes, for beginners, just have fun. Because having fun, you'll begin to like this domain, which, yeah, it's spectacular. It's pretty nice. Let's see how much time will the solving take. Around 6 minutes if it does not stop in the meantime. Do you have a question? Siti Hassan, hi. The price listed, can you see it? The price listed on your website, is it for one specific project, right? Project FEA, yes, one simulation. Do you say like a package that bundles few projects? It would be great for a student like me. The answer is yes. Yes, mail me a list and I will also provide a discount. Because you purchase more, okay? You have the contacts page, so yeah, good luck. I will make the bundle according to what you need, and I will add up. I will sum up the total, and I will make the discount, and I will give you a payment link. Yeah, no problem. Thanks for asking. 8 minutes. All right, because we have 8 minutes, this means we have lots of time. I will put this here in order to see if it solves or not. We have lots of time to see other people's work, all right? What our colleague did here. I think he used kind of a coarse mesh. He takes it from the start. What material does he use? General. No. Only if you want to make some investigations, but no default material, yes? Copper alloy, no. Yes. Structural steel, what? The plate is structural steel and the bullet is aluminum alloy. Or copper, no, or copper, no. What was the material? Aluminum alloy. No, please, no, you're not. No. The bullet is rigid, so the material does not count at all. He is changing the material in vain. It does not matter because the stiffness is infinite, so it does not matter. Body interaction, yes. Frictionless, all right. If you want it like this, what? And here he applies what? An initial velocity? Yes. How much? Let's see. How much? I'm interested. 900 meters per second. Oh my God. Overkill. Yes. 3 times the reality, or maybe very fast bullet, maybe. He has fixed the periphery, yes. And now let's go for solving. Yes. How many minutes? Oh, 1.66 minutes. Super, yes. He penetrated the steel plate only because he has a rigid bullet and he has such a high velocity. If he had a copper bullet or an aluminum bullet, he would not have penetrated this plate because it's steel. No. But yeah, increasing the velocity, yes, it will go through everything. We will also increase the velocity in a short time in order to go through more than one plate or two. So we will also increase the velocity just for the show because it's more spectacular. Yes, it's nice. It's nice as it can be. 3 plates. I'm interested. Count me in. Time step too small. All right. What do we have here? Oh, yes. Because the elements elongate and they distort so much, we should use a much finer mesh, yes? A much finer mesh. All right, so at this moment, what I will do is, let's see, because I would like to duplicate it. In a few days, I will publish these. I will publish this on my website also for sale, and they will be called stream ANSYS files for stream 1, ANSYS 5 for stream 2, stream 3, stream 4, and you can also take a look again at what I did during these live streams. So these will not be lost, yes, they will not stay only on my computer. You can also use them after you purchase them. Where were we? Here. The thing that I wanted to do since a while ago, because there are problems with the time step, let me assign time steps. 1e minus 6, this is my preference from experience. 1e minus 9 and 1e minus 6. Feel free to read, minimum initial, whatever. Should we make maximum energy error 0 right now? Not at this moment. Let's solve with this value and see if we exceed the blocking point, which is around the 28%, yes? Let's see if we go higher, 30, 40, 50. Does it solve? I'll look a few seconds at my smartphone. No notification. Everything is perfect. It looks like it's working. So where were we? Here. Mr. Manik, what he has aluminum alloy for the bullet, and the plates are concrete. Yes, I'm interested. I'm interested. Let's see. For analysis settings, it has 8E minus 4. Yes, it's a little too high, but during given the distance, I would say. But it's nice. Yes, something else. Fixed support, yes, and velocity. Show me the velocity. Oh my God, 2,500. Yeah, it's to achieve results, no problem. Yes. And here you can change it to have megapascals. If you change to millimeter, you need system with millimeter. And oh my God, what is this? Oh no, oh no. So he has here 100,000 megapascals because he's using everything linear, and also these annoying inertia center mass points. Oh, it looks so awful. I mean, this mesh. Dude, firstly, refine a little, discretize. I mean, the hour, what hour I am, hour 100.5, and I discretize. And you, why are you in a hurry, and why do you present something like this? Please refine. Refine, come on, you can do better. And it's easier. Is there a bullet presentation ANSYS workbench? This needs to be seen, I think. Does it work? 22. This is, we'll have a limit point, an obstacle, I think. Soon, what? SPC material, yeah, finally SPC material. For steel, come on, decide, yes. He has a steel. Only for steel? Oh, what? Ah, and his modeling. This is made of steel. Ah, the plate is aluminum, and the bullet is made of steel. All right, who am I to judge? Oh my God, such a... This is not so important. The plate is important. Come on. Give a sizing, please. Yes, sizing, yes. No, sizing. Do we leave it like this? All right. Velocity. Yes. There is a difference between velocity and initial velocity analysis. So it stopped and it didn't exceed to 27%. All right. But what seems to be the problem? Time step too small. So when I have this error, I usually copy the number of the element, wrap up time step controlled by unstructured element. I copy it. And I will go here, right click, select mesh by ID, change to elements here, and right click paste, okay? Paste, create named selection, because I want to see what is the offending part. Create named selection. It created here a named selection, this one, and it's, the problem is with the bullet mesh. They don't like the bullet mesh. Maybe it's too, maybe? It's too coarse. All right, at this moment, I would like to introduce you to this thing, which will speed up solving, hopefully. Yeah, this is like, yeah, it's used by many people. In order to speed up solving, automatic mass scaling, yes. And you are safer if you go with 1e minus 7. You kind of wish to have an average time increment, an average time step of e minus 7. You wish this, okay? Let's see if it solves. Then we will begin to work here and to decrease this value for geometric strain limit. Clear generating data, save, solve. So in the last simulation here, it said that it will solve in around 8 minutes or something. Let's see, with mass scaling applied, let's see how long it will take. We'll have the same error, no problem, because we didn't solve the meshing, we didn't correct it, but let's see how long it will take. Now, because we have applied mass scaling, yes, it is exceeded. Please go on Google and familiarize yourself with mass scaling. There is a nice explanation here in the LS Dyno. Yeah, maybe image. It was a website which explained mass scaling. Yeah. This is the, yeah. So because we know that the speed is distance over time, this is the speed of sound in the element, yes, this is the element size, the time step, the increment, let's say, and this is the element size. And going for this, you can see that it will change the density of the element. It will increase artificially. ANSYS will increase artificially the density of the element in some portions. I want to tell you what CFL means. Courant Friedrichs Levy. Okay, these two mathematicians, more than 100 years ago, I think they debated, they established these equations. They established the use of mass scaling when performing such mathematical solving, let's say. So here they are doing some comparisons. You see? So they decrease they increase the solving time, and they increase mass scaling. Yeah, you remember before it was e minus 20, yes, and I put e minus 7, so they increased the minimum time step. Hence, the solving time will decrease. This is the purpose, to have smaller solving time. Not here, not here. 5 hours. Yeah. It can be even nicer explained, at least for beginners. Do we have something nicer? It used to be we used to have some slides, and I cannot find them at this moment. Do we have them here? Yeah, this is This is what we have. This is what I wanted you to see, this equation. Can I open image in new tab? Because I'd like to zoom in. Yeah, this is the speed, and we can take it from here, all right? And there is this equation with the Poisson ratio and the density, yes? And it makes sense. It makes sense. Why we need this mass scaling? In order to increase the time step, we need to work here, yes? Either increase the element size. This is why we make coarse. This is why we make coarse mesh, to increase the time step and have faster solving, yes? Or we decrease the speed of sound in the element, which is a property of the material, yes? We have different speeds of sounds in the material when we have different materials, steel or plastic. This is why some people also use not steel but plastic parts, you know, in their FEA in some parts, you know, everything to accelerate the solving, to increase the time. And in order, if we don't want to change the element size, if we don't want to make it coarse, then we're going to artificially change. The software is going to artificially change the speed of sound by increasing the density in some parts. Okay, it will go for the density. It will not change the Young's modulus or Poisson ratio. Yes, it can be understood. No problem. Where was I? The solution for this thing, because there is more fraction added, okay? The one easy solution for this thing is here to go and change this part scaling. Instead of 0.05, maybe to 5, 10, 50, big numbers, okay? Right click, clear generated data. It's very useful. This mass scaling is very useful. It's time saving, very much time saving. You'll see in a few seconds. So we start, well, back where we were, let's say. Let's force it a little, because there is not much difference. But let's force it a little, okay? Let's force it a little. And the forcing is this one. Let's force it to have 6. A very high time step, yes? When we're doing something like this, we'll get again the same error with the mass increase. Do you want to clear? Yes, solve. These are points and small tips and, let's say, secrets that almost nobody will tell them to you and will share. And they are not very easily found and understood. All right, ANSYS, come on. Do we have any question? It seems like, we have a reply. All right, will do, thanks. Yeah, thank you too. So, that same error again. Yes? Just for show, because I want you to see, but it should be treated with respect and very carefully in reality. Just for show, yes? You can make this maybe 100. Solve. So in the last simulation, we had around 7 minutes of solving. Let's see now how much time we have for solving. Come on. Show me something nicer. So it's a little overkill. Because it's not preferable to have such value for maximum part scaling. The default was 0.05. Let's go back to something more decent. We had 5 in the past. And here we have 1e minus 7. Let's solve that problem with the meshing. There was a problem with the meshing here. How should we solve it? Yeah, change the size. 0.6. Maybe make it 7. Save, solve. Come on, show me something nice. It's faster because we have a coarse mesh. Come on, show me the mesh. No, you don't want? You don't want. We have a coarser mesh in the bullets. This is why it's faster. Let's see if we still have that error, which is pretty annoying and not interesting. Where were we? Mass scaling. And there was this tutorial, 1,500 meters per second. And the plate was, what materials did we have? Aluminum. And the bullet made of steel. All right. He didn't show the connection because everything is default. Because this cylinder is so close to the plate, it might be a bonded contact, and he's not showing this because it might be a bonded contact, and that bonded contact should be deleted. Oh my God. 1,500. All right. And time. What? 20 e minus 6. 2e minus 5. Yeah. Somewhere there. Solve. Oh my God, the mesh is so sad, the mesh. Oh no. And I still believe that there is a bonded contact there. And he does not scale the stress, so in order to also have stress in the plate, so it looks nice. Come on. Yeah, it is something, okay? It's not perfect, but it is something. Fracture analysis of bullet in ANSYS workbench. Oh, let's see. We are more than 27%. We're on the right track, I think. What do we have here? Let's see the materials. But the quality, come on. The resolution, oh. 11 years ago, oh, okay, you have an excuse with this resolution. What material do you choose? Steel, okay. And a bullet. You only have a bullet? Come on. A bullet with something more. All right, so this is made of steel. I hope you don't leave it steel. Oh, this steel, yes, steel, all right. Structure steel, so everything is steel, also the bullet. All right, if you wanted to know, why not? Element size 0.003 what? Meter, 3 millimeter, okay. Generate mesh. Oh, why do you care about that sizing? Because you're going through the hole. Why do you care about this sizing? You can suppress this. You can, or it's not important. The box is not important. What speed do you use? 20,000 meters per second. Oh my God. This is a railgun, I think. Yeah, this is. He fixed there and he fixed the box. 0. It's a big. It's such a big end time because we have such a big velocity. It's very big end time. No, you didn't correlate it, my friend. You should have correlated with the small speed equals space over time, distance over time. So you didn't correlate it, my friend. All right. So Mr. Satvinder Dagar. What? Oh. So you didn't do anything because nothing. It's blooming there. It's nothing. Come on. Change the velocity. Yes, please. Yes, this is a nice velocity. Only. What? Why do you remove the? Come on, dude. No, come on. Please fix something. 2e minus 4, all right. And the problems appear. Yes, friend. When you try to do something good, problems appear. Hence, the conclusion. If you don't have any problems, you are not on the path of doing something good. On the path of doing something good, you have obstacles. If everything goes smooth from the very beginning, then you are missing something and you are not on the right track. In principle, it can happen that you are on the right track in life, but maybe not in FEA. Oh my God, the mesh is awful. But yeah, it's he's investigating, he's editing. My FEA stopped, I think. Yeah, we're going towards 40%. Do we have the same problem with the mesh? Let's see. Copy. We go here, right click, select mesh by ID, elements, paste, create named selection. close. And here on the name selection, we have this one. Now it's demeshing this part. Does it help if we change the mesh to be even more coarse? 0.8. Let's see. Let's see if it helps. Generate mesh. Save. Solve. So it doesn't work. You don't want to stop, but I will force you. Control-Del, Task Manager, and we're going to select one of the. Let's close Space Claim. I don't know why it's opened right now. Where is the solver? Here. ANSYS solvers auto dying, okay, and task. And it stopped. Right click, clear generated data, yes. Solve. Yes. Where are we here? Let's see this nice tutorial. More values. 1000 meters per second. Hey, you're going somewhere. Finally, common sense. Yes, finally some common sense. Look, yes. Finally, this is research. Yes, this is trial and error. Yes, I like it. All right. Підірок моделірування удара в Auto-1. Is it Auto-1 though? Let's see. Смоделіруван удар стальной бобішки у резиновую пластину. I think it's plastic deformation or something. Let's see. Rubber? What? Rubber, okay. It's not a bullet. I think it's compressing rubber, I think. Ставим начальные условия скорости болванки. I think this is maybe error or wrong. Начальный момент времени. This is a speed, maybe, yeah, 100 meters per second. This is S in Russian, yes. Let's see. 100 meters per second. Yes, perfect. Жестко закреплен наружной торти пластинки. Okay. I don't know what this means, but it's nice. It should be something nice. Ставим условия симметрии. Symmetry, yes, on those faces. Yes. I like the comments, even though I don't understand them. Результати расчет отображаем в виде деформации напряжения по мезис и скорости движения тел. Mrs. Stress something. Седуляция стандартным образом. Также запускать и анимации, которую можно сохранить в AVI file. Okay. So export to AVI. Okay. What is happening? Because it's rubber. It goes back and kind of fills the hole. Yes. It's I didn't see until now made for rubber. Yes. Lots of vibrations. Nice work. Yes. Oh, someone who approached biomechanics. Finally, contact me. Finally, biomechanics, simulation in biomechanics is such a hard domain. 8 minutes, okay. All right. So, контактные поверхности в фасеточных суставах позвоночника. ANSYS modeling. This is easier to spell, at least for me. And he has here, instead of the ligament, there is a very big ligament, let's say. He has a small spring, very nice and static. And I think he has also a spring here, I think. Spinal motion. Oh, this is cute. I think, he has 2 springs there. I think I should do something. I should do something similar. I like the spring idea. I like that he has used different materials to have for like a spongy and cortical. And also here, because there are different densities here, there are lamellas, there are different rings for the cartilage here. This is very nice. I should do something similar in the future. He has a very good model. I think we can find such model on GrabCAD, I think. Does he leave bonded contacts? Please don't leave bonded contacts. Please don't. Even though it's easier to converge, please don't leave bonded. He left bonded contacts. So the only bonded contacts should be between vertebra and cartilage. Yeah, vertebra and cartilage. There should be bonded contacts, and also there should be bonded contacts inside. Look here. Because here should be bonding contacts, because he has different material densities, yeah? So between the spongy and the cortical part, but here, of course, it should be bonding contacts also here. And also here in the cartilage, because he has 2 different cartilage densities. But in the rest, we should have usually frictionless contacts between the vertebrae, yeah. But he aimed for converging simulation. He's frictionless. Yes, finally, yes. I would have extended these faces. This is the last. This is the last. Oh. This is the last, and he should have followed it. Yeah, it's such a complex simulation. I understand that he didn't follow. It's very hard. Biomechanics is very hard. Mr. Dolivanov. Bullet CFD explained. ANSYS bullet simulation tutorial. Oh my god, let me see something else. What is this? Composite material. This should be interesting. We exceeded 40%. Now we were 50%. Yeah, we're on the right path. What is this? Oh my God! Oh my! What is this? Why? What is this? What is the purpose of this? Zero purpose, zero use, nothing. Why? This I want to see, and also this. This looks very nice. I want to do something similar very soon. This is so nice. It looks so nice. All right, and where are we here? He has two material types, I think. He has a linear material for the plate. I bet you, Mr. Ahmad, I think you have a linear material there. But yeah, the simulation principle is, it looks nice. It looks nice. What do we have here? El Makri, Mr. Mohammed. Gunfire bullet, this should be interesting. Yeah, this looks nice. This looks nice. More plates. Oh. Bullet hitting glass. Yeah, this should be interesting. 8.2 minutes. Okay. And now, which one is the culprit? Copy. I will delete this one because we don't need it. But I will go here, select mesh by ID, elements, paste, create name selection, close. This one. Come on, when will you leave me alone? When will you leave me alone? Come on. What will happen if I make, let's at least animate. Until now, we didn't have problems with this scenario. But these two, they give problems. I mean, the bullets, they give problems. But with this material, it didn't show any problems. All right, where were we? Let's change the mesh to hex, the mesh for the bullets. Let's make it hex. And maybe we get rid of those messages, of those error messages. Because surely I don't want to refine the mesh on the bullets. There is this option to refine the mesh on the bullets, and I don't want to do this because it will prolong the simulation. It will extend it too much, and I don't want to do this. Do we have something here? Yeah, this is poetry, and it's made in Autodyne, yes. It's not made in ANSYS workbench, Autodyne, okay. Yeah, this was a lot of work. Where were we here? Let's focus a little. Look at that smartphone. If we have an SMS, let me check it a little. replied, let's see. What I said that I will change the method to X. Let me keep my and here I will remove these bullets. How does it look like when I generate? It looks like this. Yeah, let's solve it. More solving time. Yeah, why not? Such a cute one. End time, yes. Bullet 1000 meters per second, yes. And this is all. That's so nice. It's so cute. Oh my god, it's so cute. I like this. Mr. Manik. Mr. Manik Bingra. Nice FEA. Why did you stop? He also went for SolidWorks, which is a little more is limited. So the estimation tape flow, yes. This is he took the model from Autodyne from ANSYS tutorial or something, if I remember correctly. If he would have had a finer mesh in the bullet, it would have looked very nice. Yeah, nice results, nice simulation. This is cute. This is cute. And I applied the rotational velocity, and you can see that it rotates on the trajectory. You don't see the rotation of the bullet, unfortunately, because we should go very close. It's you'll see in a few seconds that it's like a spiral. It goes in a spiral. It's nice. Look here. Yes, it goes in a spiral. Yeah. Simulation. What have we here? Do we have something nice? Finally, something that looks nice. Here is pretty primitive. I would like you to see this one. I will not be surprised if there is a bonded contact here. The mesh is a little too fine. ANSYS Nabocus and the ANSYS. Oh my god. This is one of my first simulations I made with a bullet. Make the Katamifar, yes. Oh my god, what? Why would you? And you call yourself a guru? Please don't call yourself a guru. Come on. You're offending all the gurus. Why? What is this? Please don't. No. We have also a bullet here. I want to show it to you. What? It doesn't work with the hex mesh? Ooh. 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 Why not? Let's go again. And let's do something like this at this moment. Let's change from 1.5 to 1, all right? And let's solve it again. How much? Can I make it 1? Why not? You'll see an increase in the breakage in the fracture of the plates because I made the dielectric strain limit 1. I think. The mass scaling itself, the mass scaling didn't work because we don't have elastic alloys. The mass scaling would have worked if I kept this these plates linear, the default aluminum alloy. But the mass scaling does not do so much or almost anything because there are no linear materials. What have we here? Show me. Yeah, it's nice. I like how it looks like. Normally, he wanted a perforation here. He wanted this portion cut here. He wanted a perforation, but unfortunately, the bullet is so soft that it closed. Look here, it closed. The bullet closed. And there is no perforation. A part of the plate should have gone inside here in this cavity. He should have used a stiffer bullet in order to do this, to make this shearing, to make this shearing. Yeah, nice FEA. This is a bullet in a jaw. This is an artifact. It's like an error. This is a results error. This should not be here because it isn't touched at this moment. Yes. So this is an artifact that is in ANSYS since many years. Yeah, this should not exist because the bullet is not there. But yeah, the simulation is nice. Through bone, yes, and it lodged. It gets lodged itself here in the jaw. Yeah, and here is a very interesting simulation because we have water and the bullet perforates the recipient, the tank, and the water. Yeah. For the professional eye, if you have seen it, the bullet is a little too fast, and it kind of penetrates the water. Yes, there is, but afterwards the water makes place to the bullet. Yes, I think I should have used maybe a finer discretization for the Eulerian part. Water is Eulerian, and maybe I should have used a finer discretization. Now I'm thinking that even better, and I should have used a shell here. This is a shell body, the tank is a shell body, and there is proper distance. There is always a gap to ensure tightness. Yeah. And the bullet, if I would have used a shell bullet, even though in reality there is no shell bullet, the shell bullet would have kept the distance with the water. The shell part would have not allowed the water to come to interfere with the solid. This is a very exquisite and nice detail that little people know this. But yeah, regarding coupled Eulerian Lagrangian, this is what is coupled Eulerian Lagrangian. Yeah, I have some extensive experience. Let's see what we have here. More than 52%. Yes, why not? And here, this looks very nice. In the beginning, the spikes, I don't like the spikes too much. What is the problem? Inside he has a core with hex mesh, and outside a jacket with a tetrahedron mesh. No, please, no. And the jacket goes off. This is why it's distorted so much. The speed is very fast because he has a small end time. The speed is very fast because the speed is so fast. The jacket comes off. This is stiff. It stays in place and the jacket comes off. It could have been nicer. In my opinion, it could have been nicer. With maybe a finer mesh here and a proper velocity, because this velocity is too high, in my opinion. What do we have here? I think this guy has made lots of simulations with projectiles. It looks so nice. I think I should do something similar. The mesh would have been nice too. If he had a finer mesh here, then this tunnel, this cavity would have been nicer. Yeah, it's cute. And this dude, I think, has made so much. He has did, or maybe copied, I don't know. Maybe he purchased my tutorial. What number is this one? I didn't link the page. Yes, I linked it. It's tutorial. What? didn't make a tutorial. Yes, it's tutorial 25. And he either purchased my my simulation or my tutorial, because everything, you can see everything is. But here he didn't assign the contact here. What? So here is not correct. He maybe purchased the tutorial and didn't assign the proper contact, because here we have proper contact. I did this 12 years ago. So nice try, but you forgot something. You forgot something. Yes, you forgot this side. Nevertheless, he has a cute FEA. Some cute FEA. Let's see this. This should be nice. It looks nice. Yes, it looks nice. Milling is the most used cutting method in CAM. Is it? Because a lathe is the first that was created. I think maybe lathe. Machining by lathe maybe is the most used. I don't know. It's yeah, he has done some nice simulations. What do we have here? Finally, something that works. Finally, something that works. Till the end, and we can end the stream on a happy conclusion. This is, I think, my first. No, this is my first, and this is a second simulation that I published. Bullet through aluminum plate ANSYS simulation. Yes, let's see it. 11 years ago. Come on, don't rotate so much, just animate. Yeah, it does the job. Yes, it does the job. What is this? Firstly, let me tell you, this is meshed with Cartesian elements. Can I show them to you here? Let me show them to you. Maybe in a few seconds, I'm sure. Let's wait. So we have finally a successful solve. Finally. Until the end. Come on, come on, come on. First thing that we do, we save. Save. I will show you the Cartesian mesh. Yeah, finally. Let's also show without edges and with maybe 50 here to have 25 frames per second. The bullet gets distorted and it gets flattened. Do we have stress? We have stress. Let's here put, I don't know, 500, maybe 300. So according to what I see, I sincerely don't like this this material. I think it's the Guinan material. For the plates, yes, 1100, and it's the Steinberg Guinan. And sincerely, I don't like it. This I don't like it also. It's the bilinear isotropic hardening one. Not because it has so much red, but and this looks nicer, I think. The Johnson Cook plates. All right. Anyway, this needs to be researched. Okay, so yeah, it's these are just proper my own opinions. Okay. Is the bullet displaced? No. It gets distorted so much. So because it perforated very easily, the bullet stayed pretty intact. Here it perforated slower, let's say. The plates are stiffer, so the bullet is very well compressed. And here is something in the middle, yes. The plates are not so soft, not so stiff, so the bullet is something like in the middle, let's say. What I wanted to run, I would like to run this scenario with a finer mesh on the plates, only this scenario, yes? So this is extra according to my taste. And I want you to see the with 2 elements per thickness in the plate. This is what I want everyone to see. This is very nice. Duplicate. Do we have any questions? We have some questions. Let's see. Are you an engineer from sector, or an academician, or just a tutor which has wide knowledge about FEA? Except academician, I'm also an engineer working in automotive, and I do FEA in automotive, and also I have wide knowledge about FEA. Mr. O'Connor. Thank you for your efforts. Thank you too. Let's put also heart because it's free. Yeah. So where were we? Here I would like to only one scenario. One scenario, yes. And here let's write 3 scenarios. All right. How long is the stream now? It's 2:30. Okay. Let's do it quickly. The solving should be faster because we will only keep 4 parts instead of 12. 1 bullet and 3 plates. 4 parts. All right. Where are we here? I said something like this. Box select, right click, suppress. And here I will make the mesh of the plates. Yeah, much finer. It was 0.4 if I remember correctly. Beginning with 0.4, we have 2 elements per thickness, beginning with 0.4. Oh, yes. Beginning with, but you see here, 1 element per thickness. I would like to be 100% that we have like here, 2 elements per thickness. Yes, and in order to ensure this, we're going to make 3, I don't know, 3, 8. It's pretty random, we have more. And let's make it 3, 5, or generate mesh. Yeah, we begin to have almost everywhere 12 elements. Let's leave it like this. Regarding number of nodes, 32,000, yes. Let's see how fast does it work. If it's too slow, I will use only one plate maybe. Six, maybe 4, 5 minutes. Where were we here? I promised you about the. Can I open a past FEA? Let's open this one. I don't want to interfere with these results sincerely, so let me duplicate something. Yes, of course. 6 minutes, yes. I'll move the section to be more in the middle if I can. I don't know if I can. Yes, it's more in the middle. Yeah, we can use a finer mesh in the plate. Yes, we can use. Look here. In the bullet too. But the bullet is too coarse. Yeah, but let's leave it like this. At this moment, over here. I promised that I duplicate, and I will show you, and I am showing you the Cartesian elements. The Cartesian mesh is pretty recent, let's say, yeah, 2 years ago was implemented in ANSYS, and this plate, this used to be a cylinder and was meshed with Cartesian plate. If I have a cylinder, I will show you. I don't have a cylinder here. Maybe let's suppress everything except the cylindrical body or revolute body, and I will show you the Cartesian. Let's leave it to default and see what happens. So instead of 1, can I make here, I don't know, maybe 2? No, 1.5. Yeah, it's not so nice. Let's open space game. I would like you to see a disk which is not, if the mesh size is 2 quarts, is not properly and entirely meshed by the Cartesian elements. So we have this plane. Let's move it higher. Let's split this body with this plane, and I will remove everything else. Update geometry from source. 6 minutes. All right. How does it look like? Ah, yes. So we increased the stiffness, yes, of the mesh by adding more elements. And this maybe will not touch the third plate, maybe. So which is most realistic? We should go for 2 elements per thickness on the plates and a finer mesh on the bullet. And this will ensure more reliable results, all right? And also remember about this, yes, about the quality. Remember about the quality, and in your laboratory, in your company, they should tell you what quality you should have regarding skewness, regarding Jacobian ratio, aspect ratio, and yes, there should be some standards in place. But here we're just learning. Let's how much can I put 0 default? Okay. Three. Two. Why wouldn't you? 1. He needed for the thickness. I couldn't have assigned more a bigger size because of the thickness of the plate, I think. And here 0.5, I don't know, let's see. Yeah, I don't know why am I stubborn. Maybe colleague, maybe he didn't use a Cartesian mesh, maybe. Or maybe it can be achieved only when having a square plate. Let's see. We have enough time. But nevertheless, look here. What? Now I see that the bullet is Cartesian mesh. Yeah, this is Cartesian mesh. So, problem answered. This is Cartesian mesh all the time. We do, small secret, we do Cartesian mesh when we cannot achieve hex mesh. This is a small secret, yes? It's like a small, desperate measure. I'm not saying that our colleague used it out of desperation, but yeah, it can be used out of desperation. No problem. We need to be very creative. Alrighty. Yeah. This is a Cartesian mesh for a perfectly rectangular body. So, yeah. From my experience, I know that this, come on, close. That mesh, this bullet mesh, is Cartesian. Because of these, these contours, let's say, they are made from Cartesian mesh. Very fine Cartesian mesh. All right, let's see what we have here, and we can successfully close the live stream. Yeah, nice, nice simulation. Does he have more? 600 subscribers. Oh, I think I know this guy, I think. Yeah, he has this is nice. Can we insert something like bullet? Yes. Yes. Look, the effect of not suppressing the inertia points, the inertia masses. Yeah, it looks nice. I should do also something similar. It's nice to get inspiration, and yeah, we learn more. So nice, so nice. In 3 years, no likes. Come on, why no likes? So the bolt fractures at the moment of impact. Exactly at the moment of impact, the bolt fractures. Or is the artifact the simulation, the animation error? Such a nice animation. Yeah, it's the artifact. Yeah, I know. The same error that I had on the simulation with the jaw. It's not broken. It's shown before being broken, which is an error from ANSYS animation. Such a nice simulation. Come on, how can you not like this? Either two stiff plates, or yeah, two stiff plates, because he has a nice mesh. Yeah, nice work. 67 seconds, all right. Kevlar armor versus bullet. What? Nauka это игра в Бога. Игра is a game, no? But it should be armor versus bullet, I think. And Nauka is ANSYS? Or Nauka is vest, maybe. Science. To igra w Boga. Nauka. To igra w Boga. Science is a game of God. Yes. Boga, yeah. God. Yes, and so little people know this. I agree with this. What? No plasticity? No. Kevlar 1.5 millimeter versus Magnum. Bullet. Magnum bullet. This is Kevlar, and this is the body. Yeah, Kevlar 6.5. Yeah, nice, nice comparison. Yeah, I should do something. Very nice, very nice. Come on, no more bullets. No more bullets, no more fun. Only work. No more fun. Engineer Karmilov. All right. What is this? Oh my God. Oh my God. Yeah, this is when you have very fine discretization. It looks extraordinary. God helped us, and yes, we successfully finished. I don't like the mesh of the bullet. This is why I don't want to see it in section. Where are we? Stress. Yeah. Look at the values. Look at the values. No more 1000. We had 1000 in the past. No. These are proper values. Look here. It looks so nice. Yeah. And the curve, you see the elastic domain, and here is the plastic domain. Look here, the stress. The stress curve. Yeah, let's leave it. Let's leave it on this note, and end the stream here. Thank you for your attendance. Let's see if we have another email. Work goes forward. Yeah, it's something like the show must go on. Yes. Thank you for your attention, attendance, and everything. Have a nice day. Bye-bye.